So I'm going to talk about partial monitoring, and I'm really glad to hear that so many of you know and love bandits. I just assume you love them, but I know you know them. Because partial monitoring is an interesting extension of bandits, and it's not only an interesting extension, but it's really wide open, as you'll see. There's sort of tons of open problems. It has a pretty interesting structure. So I hope that lots of you will like it enough to solve some of the problems. So it's a bit of a complicated setup. So it's like a bandit problem. It's a sequential problem where you take actions as a learner, and you're competing with an adversary. And so what happens is at the beginning of the game, which lasts n rounds, the adversary is going to choose a sequence of outcomes. And these are just a sequence of natural numbers between 1 and some uppercase e, which you know. But the adversary isn't going to tell you their choices. They do that secretly at the beginning of the game. And then in each round, what happens is you get to choose some action from one of k choices. So this part is like a bandit problem. You get to choose your action, maybe with randomization. And then you suffer some loss, which depends on both your action and the choice of the adversary, the outcome. Right? So the loss is given in this matrix, which you also know. You're given this matrix in advance. So in this particular game, you have 3 actions. You can either predict heads, you can predict tails, or you can say, I don't know. And the adversary is just choosing a sequence of heads, tails in any way they like. And if you guess correctly, then you suffer no loss. Right? If you guess heads and the adversary chose heads, no loss, it's great. If you guess tails and it's heads, then you get some loss. Or you can say, I don't know, and then you just suffer some constant loss C. Okay, so I really want to emphasize this loss matrix is known in advance. But what's not known is the choices of the adversary. Okay? And then you also get some feedback. So this is the big difference in the bandit game. In the bandit game, the feedback is your loss. You choose an action, you get to observe a loss. In partial monitoring, you don't observe the loss. You just observe some feedback. And the structure of that is given to you in another matrix, which you also know. Okay, so you know how the feedback is given to you, but again, you don't know the outcome. So in this particular case, if you choose heads as your action, no matter what choice the adversary made, you just get to see this symbol. Right? It's totally uninformative. You can't work out what the adversary did by choosing either heads or tails, because no matter what happens, you get the same symbol. Right? But you can say there's no idea, and you pay some cost to say that. You pay C. But then the feedback is actually revealing about what the adversary did. Okay, so this game decouples the loss from the observations. And this gives it sort of a richer structure than we have normally in bandits. So before I kill this slide with all the notation forever, is there any questions on the setup? Who's seen partial monitoring before? These honest hands. A few, but not enough. Good. Good. Okay.
Did you make any assumption about C? Or?
About which, sorry?
C, little c, the cost of no idea.
We're going to see what happens. Okay. If C is really small, you would hope the game is a bit easier. If it's really big, you'd hope to see it harder, and that's sort of what we're going to try and understand. We're not really talking in this talk about these particular matrices. We're going to try and solve this game no matter what those matrices are. So this is just an example game. Okay, so one other point just for clarity, this matrix of feedback, it really is just symbols. So before it was nice to see that it gives you heads or tails, but really all that matters is which elements are in a row. And we're just going to assume from now on that this is some F number of symbols. So in this case, there are 2 feedbacks possible. But it really doesn't matter what's in that table. So here's just an example. So you're a learner, and in round 1, maybe you say heads, and the outcome is heads. And here, these red columns indicate you don't get to see those things. They're happening in the background, but you're not observing the outcomes. All you observe is the action and the feedback, and you choose the action. So you choose heads, the outcome is heads, you suffer no loss, and the cumulative loss is 0, but you don't observe anything interesting. Right? And maybe after a few rounds, you're going to, I should probably try and find some information out. So you say you don't know, and now you get feedback which actually tells you what happens, but you suffer some loss. Right? And so somehow you have to balance how many times you say I don't know against the cost of the information that you gain by doing that. And of course, the goal is to make our cumulative loss somewhat small. And we want to understand in this game how the value of C, or more generally, how the structure of the loss matrix and the feedbacks matrix, how hard is this game going to be? Okay, so the first thing I'm going to say is what is the objective here? So So we're in this bandit-like setting, so normally we're going to talk about the regret. And the regret is just the difference between the losses that you actually suffer. So that's the first sum here. And then the sum of the losses that you would have suffered if you'd chosen the best single action in hindsight. Okay, so this is the regret, which is a random variable. It depends on it depends on your actions. And if you randomize, then this is going to be random. Okay, so the adversary is choosing their things in advance. Those aren't random. But the regret can still be random through your actions if you randomize. And then there's the minimax regret, which is really just the best possible regret you can get against the meanest adversary. Okay, so you choose a policy, and then the adversary is going to choose as meanly as possible the sequence of outcomes. And we want to understand, what does the minimax regret look like? And the interesting thing about partial monitoring is we have a theorem that classifies the minimax regret into 4 harsh boundaries, at least as n is getting large, which is either a trivial game where the regret is 0, so you just know what to do. There are so-called easy games, which are the hardest to work out how to play, but that's where you get square root n regret. And then there's a gap, and it goes up to n to the 2/3 regret. And then finally, there's hopeless games where the regret is linear. And okay, it seems a bit weird to have these harsh boundaries between games. You could sort of smoothly change the loss matrix, and it feels weird that the boundary is changing harshly, and that's all hidden by the constant factors here. So the constants in front of these big thetas can depend on the structure of the game. So this really is sort of asymptotic. Okay, but this is a theorem, and I haven't told you which games are easy, which games are hard, and why, and then how you should act. And that's going to be the point of the rest of the talk. So now we have this rather complicated slide explaining the structure of partial monitoring, which is actually kind of interesting, but it's a little bit messy, unfortunately. So the first thing we're going to have is we're going to have the rows of this loss matrix. These turn out to be really important. So for each action, there's some row of the loss matrix. And that's what this LA vector is, and it's some vector in 0, 1 to the e. So we're assuming here that losses are bounded in 0, 1. Okay? So that's the loss vector associated with some action. And then we're going to put a linear structure on the adversary's choices. So they're choosing, remember, this sequence IT of integers. And we're just going to let UT be the standard basis vector with the IT coordinates switched on. So that's what this UT is. And this lets us write the regret with this linear form, right? So this inner product between the loss vector of your action and the choice of the adversary, that just boils down to selecting the right coordinate of the loss matrix. But we can see now when we're comparing to a single fixed action, we can bring the sum inside the inner product, and you realize what you're really comparing against is the inner product between the loss vector and the average plays of the adversary. So that's some point in the simplex, and that's sort of the thing you want to understand. Ideally, you would know what that is, and then you could play optimally. And that suggests that sort of the important thing is, how does the simplex split up in terms of which action is optimal where? And this is what we call the cell decomposition, which splits the simplex. This PD minus 1 is the simplex into when is an action the optimal action. And sometimes there can be multiple. So CA is the set of choices of the adversary playing on average where action A is optimal. Right? So this is the set of the U's where my inner product with action A is as good as all of the others. It's equal to the minimum. Okay, so this is called the cell decomposition, and it forms a polytope of the simplex. So here's the simplex here with some example game which has 5 actions. And we have five cells in this decomposition, C1, C2, C3, C4, and C5. And you can look at this. This is in E is equal to 3, so the simplex is 2-dimensional. It's just an equilateral triangle. And some of these actions you can see are sort of probably going to be better than others. So there are actions that we call Pareto optimal, which in this figure is C1, C2, and C3. So they're the set of actions where the dimension of the affine hull of the cell is equal to E minus 2. Okay, so they're essentially the ones which are optimal on some reasonably large subset of the simplex. And then we have the so-called degenerate actions, which is the one where the dimension is less. So for example, C4, this action is only optimal on some low-dimensional subspace, and C5 is optimal only at a single point here. And you can have actions that are optimal nowhere, and they're actually called dominated actions. So this is the cell decomposition. And then we need a notion of neighbors. So which actions are close to other actions? And there's two concepts we're going to need. One is this n of AB. And this is only defined for the actions A and B that are optimal sort of in big places. So C1, 2, C3, and C3 this case, Pareto optimal actions. And that's if you just take two neighbors, NAB is the set of A and B, so 1 and 2 in this case, and the degenerate actions that lie between them. Okay, so this definition here makes it look kind of complicated. All this really is saying we have C1 and C2. Oh my gosh, this is a big race between getting through a slide and then typing in my ridiculously long password. All right, so what we have here is we have one degenerate action that's between C1 and C2. Okay, you look at the intersection of where C1 and C2 are optimal, and you see, is there some action that has that as its cell? And indeed here there is C4, so this little neighborhood that we call it has C1 and C2 and C4 in it. Okay? And then we have, say, C1 and C3, that would just be a little neighborhood, but there would be nothing in between, right? This C5 action is not big enough. It doesn't have a subspace that's E minus 2 dimensional. Okay, so this is telling you which actions can be kind of similar, right? So these two can be hard to tell apart if the adversary is playing close to this boundary here. And this turns out to be really important when you're analyzing these games. So the neighborhood structure is one important piece of the puzzle. So any questions on this? Okay. So the next question here is what does this neighborhood structure depend on? Well, it actually only depends on the losses. There's nothing here about the feedback. So the next important thing is how does the feedback influence things, and how do we estimate stuff? And the first observation that you should make is that there is no hope to estimate the losses in this game. And there are very easy games to play where you cannot estimate the losses. And that's a bit different from the bandit game. In a bandit game, you're just going to estimate the losses using importance weighting or something like this, and everything works out. In partial monitoring, it's really easy to construct easy games where that's not true, and here's one at the bottom here. So we have a loss matrix where you have two actions. And if I play, say, action 1, I actually can't tell the difference between these two coordinates. The feedback is the same. So no matter if the adversary is playing here or here, I don't get different feedback, so I can't tell. But it actually doesn't matter, because all I care about, if I want to minimize the regret, is to make my loss not too bad relative to the best arm. So all I really care about is loss differences. And in this case, we see 1, 0, the difference is 1, 2, 1, the difference is 1. So even though I can't estimate the actual loss, I don't know if it was 1 or 2, I can estimate the difference to the alternative action. Okay, so in partial monitoring, you don't estimate losses, you estimate loss differences. That's the first important thing. See what I did there? So it only depends on the loss differences, and how are we going to do that? So in each round, if you think about, say, EXP3 as a bandit algorithm, it randomizes over the actions, and then it does importance weighting, basically. That's what all of these algorithms do. And we're going to do something similar, but the importance weighting is just going to be defined abstractly in does there exist some estimator that satisfies the properties that we need, which is this V function. Okay? So we care about estimating the loss differences between some possibly optimal actions A and B. And what we're going to say is that they're globally observable if there exists some loss estimator function that's going to let us do that. Okay, and what is that thing? It's a function from the action and the feedback that you get to some real number. And then what we want is we want the sum over all of the actions C that we could take. So this is the action that you actually took is what it's going to be. And then we have this function V of C and the feedback. Okay, this should equal the loss difference no matter how the adversary played. This is sort of the condition that we need if we want to be able to estimate the loss differences. And this is captured by this formula, so we can estimate this difference here using delta hat. So it's just importance weighting, right? We have the v, we divide it by the pt of at. That's the probability that we choose action at in round t. And if you plug in this formula and then you take the expectation, this is coming out as exactly being the unbiased estimator that you would like and that you have in a bandit game. Okay, so we're just going to say they are globally observable if this property is satisfied, all right? If there exists some function, and we're going to sort of go no further than that. Maybe go a little bit further if there's time. Okay, so then global observability is one thing, but local observability turns out to be really important, which is, can we identify the loss differences for actions by just playing those actions and maybe some degenerate actions in between, right? So we're saying they're locally observable if I can choose this function v so that it's 0 if I play an action that's outside of that neighborhood. Okay, so then we're saying it's locally observable. We can learn about this loss difference from just playing local games. Okay? And of course, we're going to say a game is globally or locally observable if all pairs of neighbors are globally or locally observable. So we want all pairs of neighbors to be locally observable for a local game. Okay. So we're at last done with like the endless stream of definitions for this thing. So is it all clear? We want to estimate loss differences and basically do exponential weights. So now I can tell you the classification theorem, which tells you which games are hard and which games are easy. And so the first one is very simple. If G has no neighboring actions, then the game is called trivial and you can have 0 regret. So why is that true? Well, if you have no neighboring actions, that means the whole simplex is covered by just one cell. You just choose that action and you play it every round and you have 0 regret and you're done. Okay, so that's the really easy case. Then if there are neighboring actions, we're going to get a square root regret if the game is locally observable. If it's not locally observable, then it's going to be an n to the 2/3 regret if it's globally observable. And if it's not even globally observable, then you have linear regret. And that's the hopeless games. Okay, so this is the classification theorem. And you can see that there are like 6 pieces of this puzzle to put together this theorem. And almost all of them can be done long before we came along. So the upper bound for hard games is by Niccolò and Lugosi. And then we have various other people filling in these gaps. The only thing that's missing is if you have degenerate actions and you want to have an easy game, what should the regret be and what's going on? So in this sort of new work, we're proving basically that for easy, i.e. locally observable games with degenerate actions, indeed you live in this square root n region here. So this is the new contribution, as well as a bunch of simplifications of some of the existing results. Okay, so the result that I want to focus on particularly today is this one here, that if you have a locally observable game, how do you get a square root n regret in the face of degenerate actions? Okay, so here's a little example in this heads and tails game about when is it locally observable, when is it globally observable. And as you might guess, it depends on what this value of C is. So it turns out that the critical value is 1/2. If C is bigger than 1/2, then if you look at the cell decomposition, it looks like this. C is bigger than 1/2. It's actually never optimal to say I don't know. In hindsight, that's not the best optimal action. And so then you're choosing these two things are neighbors. You're trying to decide between these two things, but the only way to get information is to play some third action, the I don't know action. So this is sort of the typical hard game case. On the other hand, if this epsilon here is equal to 0, or it's positive in this case, so C is smaller or equal to 1/2, then you're in the easy regime. Okay, so here suddenly sometimes it actually is a good idea just to say I don't know in this slightly weird setup of the game, the very easy, nice one. And now these two are neighbors because you can indeed learn about the loss differences just by playing these two actions. And similarly, these ones. So you have local observability, and you should expect this to be an easy game. And the case where C equals 1/2, is like where it is optimal to play this no idea action, but only if the adversary is exactly playing at one half themselves. That's the case that we didn't understand until now. And that's the case where we're going to see, indeed, you can get square root in regret in that kind of game, and in fact in every locally observable game with degenerate actions as well. So to tell you why the easy games are hard, I'm just going to give you the proof for the hard games, and you should easily see, like, what is the problem? Where does the problem come when you're trying to get a good regret for partial monitoring? And the idea here, so this is sort of Nicola's algorithm, is you just do exp3, but you estimate loss differences instead of having the losses that are given to you, and you add lots of exploration. Okay, so this is the exponential weights algorithm, and then we mix a bunch of extra exploration in. Okay, so in each round we compute this distribution, we sample our action, and then we're going to estimate the losses using our God-given loss estimator functions. And eta here, of course, is the learning rate, and gamma is some exploration parameter, which we'll tune soon. Okay, big scary analysis, but actually it's not so bad. So basically what we have is we have the regret. And then the really easy point, we just add and subtract the loss of some baseline arm B, right, which we just choose in advance as some potentially optimal arm, but we don't really care. All this lets us do is write down the important thing, which is the loss differences. Okay, so here we have a loss difference, here we have a loss difference. We can estimate these things. And then we plug in the bound that you get if you just do the exp3 analysis. There's nothing fancy here. It has these two terms that you normally see in the analysis of exp3, which is this term here, which penalizes you if your learning rate is too small, i.e. you just don't learn enough. And it also penalizes you if your learning rate is too big, because then you have a very high variance. And this term here is essentially your variance term, and this is the thing that we have to control. And now we just start subbing in the definition. So this delta hat, we substitute in our v. So this is just an equality, nothing fancy. And we're going to assume now that these v's have some bounded supremum norm. Okay, and this gives you some hint about how you might choose the v, if you have a choice, which you do, is to minimize that supremum norm. So you would like to choose the v's, at least if you believe the analysis, to make this as small as possible. Okay, so then we can just get this v squared out here, and we're left with this term. So in the normal bounded problem, what do you have instead of this term? You don't have PTA divided by this thing squared. You have PTA and then an indicator function of did you actually play A. Right? So that means that what you have here is A, and here you have little a, and you have just like, did you play that action? And then you get some cancellation. In this general partial monitoring game, you don't get that cancellation because you have to learn about other actions by playing different actions. This is the difficulty that you face in the bandit game. And so the best thing we can do really is well, we can pull out one of these. We keep one of these here. And then we just bound one of them by gamma, or gamma divided by k, right? We have this fixed added exploration. We know that PT of AT is bigger than gamma on k, no matter what action it was. And so we're just going to do that. We get this k on gamma term here. And this is what kills you. This is what makes your regret enter the 2/3, because you really have no way of controlling these probabilities. Okay, and now we're really in the simple world. So now we sum over these PTAs, which of course sum to 1, and we just get the inverse of these. And if you take the expectation of that, then it's just k. Okay, so then you get this messy looking expression in terms of eta and gamma and n and k and all of these things. And if you optimize the parameters, you end up with gamma is n to the minus 1/3, and eta is n to the minus 2/3, and you get this n to the 2/3 regret. Okay, so this is where the n to the 2/3 regret comes from in partial monitoring games. And now what we have to do is somehow exploit the fact that if the game is easy, we can get a smaller regret. Okay, so the idea is basically a localization argument. You want to do exponential weights, but you only want to do it where you can get small variance. And to do that, you do it in local games. So we're going to maintain a number of exponential weights algorithms over little local games. And then we're going to combine them in some clever way and only ever estimate losses locally. And this is a big variance reduction. So the algorithm is based on an algorithm called neighborhood watch, which we make some improvements on and some corrections, but otherwise it's quite a similar idea. And I'm going to start without degenerate actions, which is weird because it's part of the contribution. But I think it's more interesting to actually try and understand what's going on. If we run out of time, then so be it. How am I going for time?
Still have 15 minutes.
15 minutes? Oh, good. Yeah. So this should be fine. OK. So here we have a neighborhood graph. OK. So what this graph is showing is there are a bunch of nodes which correspond to actions. And we have a line between them if they are neighbors. OK. And the black actions are degenerate. You can just actually assume that there are no degenerate actions for now. OK. So we have this graph. We have two actions are connected if they are neighbors. And a local game is just an action. So the local game around this action k is just its set of neighbors and k itself. Okay, and you have a bunch of those. For each action, you have some local game. So for this one, we have a different little game here. Okay, and what we're going to do is for each action, for each of these possibly optimal actions, we have an exponential weights distribution, which is just saying, how should I play if I'm playing in this little local game? I don't care about the bigger picture, just within this local game, what's going on. And this ZSKA is like the loss difference estimator for this weird weighted thing. And we'll see why it's a weighted difference between the losses of action A and action K shortly. But it's this weighted loss estimator. And then the big trick is we have to combine these exponential weights distributions together in some way. And we're going to do that by choosing PT as being the stationary distribution of this matrix QT, right? So QT is actually I guess a right stochastic matrix. And so we can define a stationary distribution with respect to that. And people ask why do that. So one little intuition for why this kind of might work is what is the exponential distribution saying? It's saying if I'm at k, maybe I have it's going to try and find like the neighbor which is the best, or maybe k itself. And so this defines a random walk on your graph. And the stationary distribution, you hope, is going to sort of lead you towards the optimal action. That's the wishy-washy explanation. And then the other explanation is just that it works. So this is not my idea. This is from the original neighborhood watch paper. So it's a pretty cool trick. And then at the end, we mix some exploration in, which is not so important. OK. So there are two parts of this argument. We've defined the local games. To prove it, we need to have a localization to somehow connect the regret that we get in each of these local games to the big picture. And this is this lemma here, which is saying if we take the inner product, the difference L and L's A star being the optimal action, this difference we can bound by some potentially very large constant that only depends on the game. So it doesn't depend on U or A star or anything like that. It just depends on the game. Times some local difference, right? So remember, NA is the neighbors of A and A itself. So if we have this claim, what we can say is we're going to bound the regret in terms of a sum of local regrets. And this is the important thing to apply the standard analysis of the regret for the local games. Okay? And the proof of this claim is not too hard, really. We're just going to say, well, we're looking at this U here. And this is the cell corresponding to action A star. And then we can take some centroid and draw of some action A and draw this path here. And either two things can happen. Either A star is actually the neighbor of A, in which case we're fine. Then this is definitely true. Or it's not, in which case there's something in between. And then the picture on the right is kind of giving what's going on here. We have some concave function, which is the actual loss that you suffer for each U on that path between the two things. And there's some barrier that's separating them. And this is the action which is going to be sort of, except for maybe this very large epsilon, the good one. Okay, so this is the localization lemma that lets us turn a global picture into a local picture. Okay, so how do we use this lemma? Well, it's pretty simple. We just use it and rewrite the regret. So So here we have TA is going to be just the number of times that you chose action A over all iterations. So we write the regret, and we just separate it out. When did we play action A? And we sum over the actions. And this lets you bring inside these UTs inside the inner product. And immediately we can just apply our lemma and then unroll this decision. And eventually you get 1 over epsilon times the sum of these local regrets. Okay, so this phi here is some function which you don't know, which selects the best neighbor of each action that you chose. Okay, so we've bounded our local regret in terms of still something we haven't quite split it up into the games yet, but it's at least local, right? We only care about the neighbors of the action that you play. So this is the first important step. And now we're going to bring in the local regrets. Okay, so now the idea is to apply a Hofdinger-Zuma. And this is sort of the new part of the analysis, although it's not super complicated. So here, this AT is being randomized, right? You're choosing your distribution PT as being the stationary distribution. It's a randomized thing. And here we have a sum of randomized things. Let's just say for a fixed phi. So this is going to be a martingale difference sequence. We can apply our Hofdinger-Zuma to say that except for some relatively small additive term, importantly it's a square root n additive term, we can put in the sum of the conditional expectations in instead. Okay, so that's what the first line is. And then the second line is we're just going to use the fact that P tilde is chosen as the stationary distribution. And here I'm making some approximations. So remember that PT is actually added some uniform exploration, but the approximation is good enough. You don't add that much exploration that this approximation is a problem. It's just like a constant factor in the regret in the end. And then this equation here is just what you have by definition of the stationary distribution. Okay? And now we really do have the sum of the local regrets version. So now we've got the sum over all the actions, and then in here, this is like a regret where you're playing an exponential weights distribution QTK, and the loss suddenly has this PTK appearing here, which is why we were weighting the loss estimates by PTK. And so this term here is your loss. Okay, so this is really just a regret of an exponential weights algorithm. And so now we can bound each of these RNKs in this term here, and we will be done. We'll have our regret bound. Okay, so this step is not too hard. It's really just repeating the analysis that we did for the hard game, but suddenly we're going to see that the variance is enormously reduced. We don't have to resort to just having this one on gamma anymore. We really have some good cancellation going on. So this is the standard regret analysis that you get if you run EXP3 or the EXP3 gamma or whatever on this sequence. So now we just have to bound this term. It's exactly the same as what we had before. But now our loss estimators, because we have this local observability property, we can exploit that fact because they're going to be 0 a whole bunch of the time, right? So now we're just going to look at this second term. And the first thing that we do is we get this v squared. We bring that to the front straight away. So again, we're using the fact that the norm of the v's is bounded by v. But now we're using the local observability, which says, well, the VAB, our estimator function, is only going to be non-zero if we're choosing either action A or action K. Those are the only two choices. And so now there are kind of two steps to get this one here. There are two cases. So what are the two cases? Either you chose action AT to be A, or you chose it to be K. Otherwise this indicator is going to kill you. Okay, so if you chose it to be K, right, then we have PTK here, and it cancels one copy of this here. And now you're summing over the A's, and this disappears here. And indeed, you would get PTK here appearing. So that's one case. The other case is where you played A. AT is equal to A. So then you only have one term appearing in the sum. And now you can use the definition of the stationary distribution to say, well, if AT is equal to little a, PT of A is definitely bigger than QTK of A times PTK. Right? It's bigger than the sum over all k's of those things because of the stationary distribution property. And so again, you get this cancellation. And I'm not sure why this 2 is here. The 2 normally appears when you make some approximations between the p's and the p tildes, then you end up with a 2. So I think that's where that's coming from. And now we are done, essentially. We have this ptk appearing here, and we can bound the expectation or the conditional expectation of 1 divided by this thing by k, as we did before. And now we have a bound on the local regret. And the bound on the local regret depends pretty nicely, so we have just log k divided by eta. And then here we have a k, which is sort of coming extra, but no gamma. There's no gamma appearing in this expression. And this is the thing that we've really saved. Okay, and there's the sum t equals 1 to n of ptk, which is pretty convenient because we want to sum these local regrets over the k. And that's the next step, so this is the last part of the proof. This is sort of what we've shown already. And we have a bound on the expectation of r and k, and here we have the sum over k's of ptk. So when we put these together, they just disappear, and we just get n. Okay, so in the end, we have a bound that looks like this, which looks very familiar if you're a bandit person. The only difference is now we have this k appearing here, which means when you optimize the eta, you have a k linear term, whereas in a bandit case, you have a square root k. So this is a price that we're paying for this localization argument, and we actually don't know if that price is necessary or not. Okay, so the other price, of course, that we have is this epsilon, which can be arbitrarily small. And that's maybe a big penalty too. So I guess I have 5 minutes, right? Good. So I'm not going to tell you how to do the proof for the degenerate case, but like when you have these degenerate actions, you have to use them potentially to get information. And we tried the naive thing, which is, well, if you've got a degenerate action, then actually you can write its loss vector as an average of the 2 like Pareto actions that surround it. And then you could just estimate its losses and just throw it into the exponential weights and hope everything works. And that doesn't work. That actually has too much variance. And so the annoying thing you have to do is you have to sort of rebalance this stationary distribution. So you do everything as normal, but then you rebalance the stationary distribution towards the degenerate actions just a little bit. You give them just enough mass that your variance isn't too bad, but not enough that your regret becomes really high. And these are the conditions that you have to satisfy. And if you do that, then you can run through exactly the analysis that I did before. And basically, you get 1 extra factor of k. Right, I won't bother going through these slides, but here we had in the previous one just terms that appeared like this. And now we have an extra k here. This ultimately makes the bound k to the 3, 2 v square root n instead, which is a little bit worse. OK. So I want to say just 2 things about this. So first of all, we have a high probability bound. So if you modify the estimators using exp3p analysis, and then you do all the machinery, then you get a high probability bound on the regret, which is great. I think the important thing is that we should actually be bothering to do this, or at least acknowledging that it's a good idea. So who wants to guess what the variance of exp3 without doing this is? So it was recently noticed by, well, not recently, in 2005, Gilles wrote in his PhD thesis that you don't need any exploration at all if you do exp3. And the variance of that algorithm, if you do no exploration, is order n squared. Okay, so with a constant probability, it suffers linear regret, exp3 with no exploration, despite having optimal, essentially, expected regret. Because it can get negative regret, and these things balance out exactly. So you can get really terrible variance. If you add exploration, then the variance is n to the 3 on 2. Okay? Whereas if you just do exp3, point p, then you have variance n, which is about the best that you can expect. So this is, I think, actually important to do if you can, or at least say that you can do it somehow. OK, so the last thing is there really are like just tons and tons of open problems. So this full classification sounds like it's really complete, but it's really only the beginning. And there's tons of stuff we have no clue about. So for example, hard games, these enter the two-third games, they're only hard if the adversary is as mean as they can be. If the adversary is playing on the boundary of some locally observable actions, you should get square root and regret. But we don't have algorithms that do that. We don't have algorithms that adapt to that kind of data at all. The second thing is we really have limited understanding of these game-dependent constants. So you saw, for example, v appearing in the bounds, and v is just like the supremum norm of some estimator function that you would assume existed. How big can v be? So we were able to show that if there are no degenerate actions, then v is at most f, the number of feedbacks, or f plus 1. But if there are degenerate actions, it seems like it can be as big as 2 to the number of degenerate actions. So that's pretty bad. But then you can ask, is v a real thing? Should the regret really depend on this quantity? And we have no clue there either. Then there's asymptotic and phase transitions. So this epsilon appearing in the bound, this 1 divided by epsilon, we know that disappears in the large n regime. If n gets really large, then at least for practically all games, you have a square root n bound that doesn't depend on epsilon. But we don't know anything about the transition, and we don't know how to get that for all games. And then, of course, you would like one algorithm to rule them all. You don't want to have an algorithm for hard games, an algorithm for easy games. You just want an algorithm that does something good. And we really don't have that either. And the last thing is there's some advertising. So with Java, we're finally finishing, we hope, in the next few weeks, a new book on bandits, which also covers partial monitoring and even MDPs. Java will never say no, so it gets longer and longer. But hopefully it will be done soon, and then I hope we will enjoy reading it. It's going to be free on the blog that you can look at here. So thank you for tolerating, and questions.